Hi, and welcome to another Dante tutorial. This time we're going to show you how to simulate the quench hardening process with a static structural model in Ansys using Dante to predict stresses and distortion. This video is a continuation of the previous gas, carb, and quench hardening thermal model tutorials, so make sure to check those out before I get started. Links in the description below. Going to start by dragging over a static structural analysis system and placing it on the project schematic. I'm also going to rename this module to Oil Quench Stress Model. Then connect the ring slice mesh we previously made to the model. We also have to import the thermal solution from the previous tutorial to the setup. This will be used in the temperature history to drive the stress model. Turn on Dante Act under Extensions and then double-click Model to open Ansys Mechanical. Once Ansys Mechanical is open, go to the Home tab and click Units. Make sure units are set to metric, millimeters, kilograms, newtons, seconds, and Celsius. Also confirm that the model looks correct and that it still has the name selections and inflation layers of the mesh. Click on Dante Model and select Stress. Click Static Structural in the project tree and then change the environment temperature to 20 degrees Celsius. Next, we're going to define the processing steps. Click Analysis Settings and set the number of steps to 7 and the current step to 7. This is important since step times need to be entered from highest to lowest. From here, I'm going to change the step end time, initial time step, minimum time step, and maximum time step according to this table, while also setting the auto time step to on, defined by time, and the carryover time step to off. These processing steps are used to calculate heating, transfer, quench, air cool, and temper. Next, let's assign the material by going back to the Dante tab and clicking Material. Click Material in the project tree, and then click Geometry, selecting the whole part as a geometry and clicking Apply. For this tutorial, I'm going to assign the 1020 steel by setting the material grade to S10XX as the material. Change total weight carbon fraction to 0.002 to set the base carbon. From here, we're going to define the control file. Click Model Control in the Dante tab, and we're going to click Kinetics Mode Table and set the Phase Transformation Kinetics Mode on steps 7 and 6 to -6 to include the tempering effect. Click Apply. Next, I'm going to define the frequency that results will be written out at each step. This is done by going to the Dante tab and clicking the Output Frequency button. Click on Tabular Data, and for this tutorial, I'll leave it as a default of 10 for each step and click Apply. Next, I'm going to add the carbon profile generated from the carburization model. Click on CN Profile from the Dante tab and set the number of carburization profiles to 1. Then, I'll click Carburization File and then find the .cbn file. In this case, I'll go to my working directory, then under Dante's _ file, select the CBN file. Under Carburization/Nitrating Activation Table, I'll select Tabular Data and then set the carburization under Step 2 to 1 and hit Apply. Click on Imported Load in the project tree and select Imported Body Temperature. Set the source time to all, and then right-click Imported Body Temperature and select Import Load. For the mechanical boundary conditions, parts should be constrained to prevent rigid body motion while still being allowed to deform under thermal and phase transformation strains. For a sector model like this ring slice, the internal faces should be fixed to prevent displacement in the normal 2 direction. A node on the part must also be constrained to prevent axial displacement. From the Environment tab, add a frictionless support and a displacement object to the project tree. Under Frictionless Support, I'm going to choose both of the internal faces of the ring slice and click Apply. For displacement, click the yellow box next to geometry. Also, toggle node to select a node from the model. Select the bottom left node and click Apply. Set the Y component to 0, meaning that the node cannot displace along the global Y axis, which is aligned axially with the part. Now we're ready to run the simulation. Click Finalize Model Settings and right-click Solution in the model tree and click Solve. To evaluate a stress state, right-click Solution and insert Stress and Normal. Click on Normal Stress and set the orientation to Z-axis. Due to the alignment of the ring slice internal face in the global coordinate system, evaluating the stress along the Z direction represents the tangential or circumferential stress state. Right-click Normal, Stress, and select Evaluate All Results. This result is evaluated at the final step and final time, representing the residual stress after processing. Distortion can also be evaluated by right-clicking Solution and inserting Deformation and Directional. Right-click Deformation and evaluate. Due to the orientation of the part in the global coordinate system, the deformation along the x-axis represents the radial displacement. This is the final radial distortion of the part after processing. Stress, distortion, as well as other results can be retrieved at different saved increments of the process from the tabular data table. Several results can be evaluated, including stress, deformation, and all the DANTE results which were available in the thermal model, such as phase volume fraction, hardness, carbon, and temperature. Lastly, don't forget to save your work. And this concludes this DANTE tutorial. If you have any questions, feel free to comment down below or send us a message at support@dantesolutions.com. Thank you for watching and happy simulating.